My name is IBM and I'm taking you through circular motion. I'm solving the past paper questions. Do not forget to download the document from the website. The link is in the video description where you can find the documents. You can decide to download the question paper or the past paper questions only, or you can decide to download the one which has solutions so that you can go through the solutions which have been detailed and which have been clearly typed. Okay, so without wasting time, I'll take you to the question paper or to the questions. And I think in part 3 we stopped on page 15, so I'll go direct to page 15. Okay, so I think in part 3 we must have stopped there. So this is going to be part 4. This is part 4. So this is part 4. And in part 4, we are going to start from page 15. Actually, page 16. Okay, question 15. A circular metal disc spins horizontally about a vertical axis. It is spinning horizontally about a vertical axis. A piece of modeling clay is attached to the disc. For the instant when the piece of modeling clay is in the position shown, draw on the figure 1.1 an arrow labeled V showing the direction of the velocity of the modeling clay, an arrow labeled A showing the direction of the acceleration of the modeling clay. Of course, to explain this, we know that the velocity for circular motion, the velocity is always perpendicular to the acceleration or to the centripetal force. The centripetal force and the centripetal acceleration always point towards the center of the circular path. Therefore, for starting with with A, I will draw an arrow pointing towards the center using a ruler. Draw an arrow in the center of the modeling clay, pointing towards the center. And I'll label this A. Then, because the velocity is always perpendicular to this, then I will draw another arrow which is at 90 degrees to this. I think I should get a ruler. So V and A must be at right angles to each other. So I want to try and make this to be 90 degrees to the other one. Use a ruler, of course. I don't have a ruler now. Okay, the essence is that these two should be at 90 degrees. So this will be A, and this is V. Okay, so note that the velocity is always perpendicular to the centripetal force or perpendicular to the centripetal acceleration. And the centripetal acceleration, just like the centripetal force, they point towards the center of the circular path. The metal disc in the figure 1.1 has a radius of 9.3. The center of gravity of the modeling clay is 1.2 centimeters from the rim of the disc and moves with a speed of 0.68 meters per second. So let's first get the radius of the path. So because this is at a distance of 1.2, then it means the radius of the circular path is going to be 9.3 minus 1.2. The modeling clay is not on the surface, it's not on the edge of the disc, it's just at a distance of 1.2 from the edge. So the radius of the circular path in which it moves is 9.3 minus 1.2. Okay, so we can now calculate the angular velocity, omega. We know that V equals to omega times r, and we have seen that the radius is 9.3 minus 1.2. I think this is 8.1 centimeters. So omega is equal to V over R, which is going to be equal to 0.68 divided by 0. Oh, it is 8.1 times 10 to the power of minus 2 to change it to meters. So 0.68 divided by 8.1 exponent minus 2. So that is 8.395. This is radians per second. So this gives us 8.4. Then calculate the acceleration A of the center of gravity of the modeling clay. So of course the acceleration is the centripetal acceleration, which is going to be V squared divided by R, which is going to be 0.68 squared divided by the radius, which is 8.1 times 10 to the power of minus 2. Or the centripetal acceleration can be got from omega squared times r, where you just multiply 8.4 by r. So this one is 0.68 squared divided by 8.1 exponent minus 2. That is 5.71 or 5.79. 709, not 79 meters per second squared. Or you can use this method, which will give us also 8.395 squared times r, which is 8.1 times 10 to the power of minus 2. And I'm sure this gives you the same thing. So I'll just write here 5.7. A second piece of modeling clay is attached to the disc in the position shown. Okay, it's in a new position, which is even closer to the center. The second piece of modeling clay has a larger mass than the first piece. Remember, the centripetal acceleration is not dependent on the mass. By placing one tick in each row, complete the table to show how the quantities indicated compare for the two pieces of modeling clay. The first one is the angular speed. Let's start with the angular speed, which is omega. Of course, we know that the angular speed, omega, is the rate of change of the angle, so that is delta theta, delta t, but angular speed is also equal to 2 pi divided by the period. And the angular speed, therefore, there is no way it is depending on the mass. So we are seeing it does not depend on the mass. Therefore, it is going to be the same. The angular speed is going to, the angular velocity is going to be the same because it does not depend on the mass, even if they have different mass. It is not also depending on the distance from the center, so does not depend on the mass, does not depend on the distance from the center. Then number 2, the linear speed, that is V. The linear speed V is equal to omega r, but remember omega is the same. Omega is the same. So this implies that V is directly proportional to the distance from the center. And R for the first is greater than R for the second one. R1 was greater than R2. So it means v1 is greater than v2, or v2 is less than v1. So the linear speed for the second piece is less than, or v2 is less than v1. The linear speed for the second piece is less than that for the first one. Then acceleration. Acceleration equals to v squared over r, which is the same as omega squared times r. Remember, v omega was the same. Omega is the same. Therefore, this implies that acceleration is directly proportional to r. And you notice that r2 was less than r1, which means that the acceleration for the second one is going to be less than the first acceleration, a1. So this is going to be less than the first piece. A metal wheel consists of an axle A, 8 spokes, and a rim as shown in the figure. Okay, so we have an axle at the center, and we have a rim, and we have 8 spokes. Point X is on the rim at the end of one of the spokes. The rim has a radius of 0.85 meters. The wheel is rotating clockwise with an angular speed of 140 radians per second. For point X, determine the speed. So we know that the speed is equal to angular velocity times r. The angular speed is 140 times the radius, which is 0.85. This gives us 140 times 0.85. That's 119 meters per second, or right here 120. Then the centripetal acceleration, of course, the centripetal acceleration is equal to v squared over r, or the centripetal acceleration is equal to omega squared r. So this is going to be 119 squared divided by 0.85, or 140 squared times 0.85. I'll check the calculator. 119 squared divided by 0.85. That's 16,660, which is 1.7 times 10 to the power of 4 meters per second squared. And I'm sure this is the same, 1.7 times 10 to the power of 4 meters per second squared. There is a uniform magnetic field of flux density 0.18 teslas into the plane of the page. State Lenz's law. Of course, this is now in magnetism. Lenz's law states that the direction of the induced EMF is such as to produce effects. The direction of the induced EMF is such as to produce effects that oppose the change causing it. You will find this question again in magnetic fields, especially for the next parts. Show that the time taken for point X to complete one revolution is 45 milliseconds. In other words, finding the period. Period is equal to 2 pi divided by omega, which is going to be 2 pi divided by 140, and this gives us 0. Let's check. 2 pi divided by 140, 0.44 0.49, that is in seconds, 0.0449 seconds. In milliseconds, you multiply this by 1000. This is going to be 44.9 milliseconds, which is approximately 45 milliseconds. Okay. A small mass is attached to a string. The mass is rotating about a fixed point P at a constant speed as shown. So, explain what is meant by angular speed. Angular speed. So, the angle an object rotates through per unit time is the angular speed. The angle an object rotates through per unit time is the angular speed, or the angle swept out by the string per unit time. Of course, the string is going to sweep out an angle. The angle swept out by the string per unit time is going to be called the angular speed. I'm using this diagram here. Or I can define it as the rate of change of the angle by the string. Rate of change of the angle by the string. So the rate of change of the angle by the string, that is the angular speed. A horizontal flat plate is free to rotate about a vertical axis through its center as shown in the figure here. A small mass m is placed on the plate a distance d from the axis of rotation. The speed of rotation of the plate is gradually increased from 0 until the mass is seen to slide off the plate. The maximum frictional force F between the plate, maximum, that is, if we exceed the maximum, then the frictional force can no longer provide centripetal force. So the maximum frictional force F between the plate and the mass is given by that expression. F is 0.72 W, where W is the weight and M is the mass. The distance D is 35 centimeters, so that is the radius of orbit. Determine the maximum number of revolutions of the plate per minute for the mass M to remain on the plate. Explain your working. So we say the frictional force between the mass and the plate provides the centripetal force. That is the explanation. Frictional force between the mass and the plate provides centripetal force. So the frictional force provides the centripetal force, and remember centripetal force is mv squared r. So the frictional force was given as 0.72 W. This is going to be equal to mv squared over r. And of course, r is d. Radius is equal to d, which was, what was d? 35 or 0.35 meters. And we know that v equals to omega r but R is D, so this is omega times D. So I'm just going to substitute in here. So I'll say that 0.72 times W, which is mg, is equal to m, where there is V, I'm going to put there omega times D squared, divide by, where there is R, I'm going to put there D. When I simplify this further, m cancels out, and then it means omega. 1D has cancelled out, so it means I'm making omega the subject. So omega is going to be equal to 0.72 times G, which is 9.81. Then divide by 1D, which D is 0.35 under square root. So I'm going to press my calculator to get omega. 0.72 times 9.81 divided by 0.35 square root. So omega is 4.49 radians per second. Now we want number of revolutions per minute. We can first find number of revolutions per second. So time for one revolution is equal to the period, which is 2 pi over omega, and this will be in seconds. Time for one revolution is equal to 2 pi over omega, which is not going to be in seconds. The number of revolutions in 60 seconds or in 1 minute. Time for one revolution is that the number of revolutions in 1 minute. That is the same as 60 seconds is going to be equal to 60 divided by the time for one revolution, which is 60 divided by 2 pi over omega. So that number is going to be equal to 60 times omega divided by 2 pi, which is 60 times omega, which is 4.49 divided by 2 pi. So 4.49 times 60 divided by 2 pi. That is 42.89, 0.88, which is approximately 42.88, which is approximately 43. So this is per minute. So the number here is going to be 43 per minute. Then the plate in B is covered when stationary with mud. So I just had to explain whether mud near the edge of the plate or near the center will first leave the plate as the angular speed of the plate is slowly increased. Okay, so of course we know that centripetal force, the force which keeps them there, is going to be equal to mv squared over r, which is the same as m omega squared r, because we can move v, because v equals to omega r, so that is m omega squared r. So we notice that when r increases, the centripetal force also increases, which means that the centripetal force is larger at the edge than at the center. So the mud flies off at the edge first. So the mud will fly off at the edge first. So I'll say the centripetal force needed. Centripetal force increases as the radius increases. In bracket, I've shown that F equals to m omega squared r. Remember, the frictional force is not increasing. If the centripetal force increases, yet the frictional force is not increasing, it means the frictional force at the edge is less than the centripetal force, so it is going to fly off first at the edge. So meaning that the centripetal force is larger at the edge than near the center. So the mud flies off at the edge first. So the mud flies off at the edge first. The mud flies off at the edge first. So because the centripetal force is going to be greater at the edge, yet the friction force that provides the centripetal force is not changing, it means more force would be needed to keep the mud on the surface at the edge than nearer the center. So the mud at the surface, the mud at the edge of the surface will easily fly off compared to that one which is nearer the surface. A vertical peg is attached to the edge of a horizontal disc of radius r as shown in the figure. So the peg is on the edge. The disc rotates at a constant angular speed omega. A horizontal beam of parallel light produces a shadow of the peg on the screen as shown. Okay. So if this is the shadow, I'm just going to draw a right angled triangle for that. At time 0, the peg is at point P, producing a shadow on the screen at S. At time t, the disk has rotated through an angle theta. The peg is now at R, producing a shadow at Q. Determine in terms of omega and t the angle theta. Of course, we know that omega is equal to the delta theta by delta t. Since here we are using theta and t, so it means omega is simply going to be equal to theta over t. Alternatively, angular displacement or angular velocity, if this is very small and measured in radians, the sine of the angle is approximately equal to the angle itself. So angular displacement or angular velocity omega is the rate of change of the angle the object moves through pi unit time, or the angle the object moves through pi unit time. That is the angular velocity. So omega is theta over t precisely. Or you can write theta as being equal to omega times t. Then in terms of omega t and r, determine in terms of omega t and r the distance sq. So I'm just going to draw a right angled triangle because there is a shadow on the wall on the screen, which shadow is QS. And of course, this angle here is going to remain theta. This is going to be R. So we notice that sine of theta is going to be equal to SQ divided by R. So SQ is going to be equal to R sine of theta. But of course, theta is equal to omega times T. So SQ is going to be R sine of omega T. So this is going to be, so SQ is going to be equal to R sine omega T. Use your answer to A Roman 3, Roman 2 to show that the shadow on the screen performs simple harmonic motion. Of course, you will know what we mean by simple harmonic motion. But of course, for simple harmonic motion, the acceleration is directly proportional to the displacement. The acceleration and displacement must always be in the opposite directions. So of course, if you know simple harmonic motion, you notice that the equation SQ equals to R sine omega T is the solution to the equation A equals to negative omega squared x. So I will say the equation SQ equals to R sine omega T. This one is in the form x equals to x naught sine omega T. That is the equation for simple harmonic motion. Is the solution to, or is the solution of the equation A equals to negative omega squared x. This equation, an equation in this form here, is a solution to this equation here. I may just put the R, but I'll leave it as x. And of course, we know that this is the defining equation of simple harmonic motion, and A equals to negative omega squared x is the defining equation. Is the defining equation of simple harmonic motion. Of course, if you have not studied simple harmonic motion, I just added this part for completeness. I couldn't just drop it. Maybe to give you more explanation, I will consider SQ to be equal to x, and I will take x naught, or I will consider R to be equal to x naught. That means now I have x equals to x naught sine omega t. This is for those who do mathematics. The speed v is equal to dx by dt. We differentiate. This gives us x naught omega cos omega t, for those who know how to differentiate. To get the acceleration, we differentiate v, so that will be dv by dt. So this will give us x naught omega, then I differentiate cos, it gives me negative sine. So this will be negative omega sine omega t. So the acceleration is going to be equal to negative omega squared x naught sine negative omega squared x naught sine omega t. But remember, we saw that x naught sine omega t was x. So this is A equals negative omega squared x. So from this equation here, the equation SQ equals to R sine omega t can give us, or can be a solution to A equals to negative omega squared x. That's why I'm saying this shows that it is performing simple harmonic motion, because the equation is the solution of the equation a equals negative omega squared x, and that equation is the defining equation for simple harmonic motion. The disk has radius r of 12 centimeters and is rotating with angular speed omega 4.7 radians per second. Determine for the shadow on the screen the frequency of oscillation. So we know that omega is equal to pi over t, which is 2 pi f. So f is actually omega over 2 pi, which is going to be, they gave us angular velocity or angular speed of 4.7 divided by 2 pi. So I'll just say 4.7 divided by 2 pi. That is 0.748. 0.748 hertz, which is approximately 0.75. Then the maximum speed. Of course, we know that speed equals to omega times r. This is going to be equal to omega. Omega is given as 4.7. Then times the radius is 12 centimeters, which is 0.12. So 4.7 times 0.12, that is 0.5. They want the answer in centimeters per second, so I don't need to change this. I'll just use 12. So 4.7 times 12, that is 56.4. So this is going to be centimeters per second, so the answer here is going to be 56. I think that is enough for part 4. See you in part 5. I think part 5 will be the last one. Until next time, bye bye.